Alright, this is the first of probably two screencasts related to the KL divergence. In this screencast, I'm just going to be going over entropy, my new understanding of entropy. So, the entropy, I think, relates to the following problem, where we've got a sequence of characters, and each character occurs with a different probability. And we want to figure out the most efficient way of encoding this sequence of characters using sequences of bits for each character, right? So you might, i.e. Huffman codes, as an example. However, we're going to kind of do the continuous case to this problem. Right. And so in terms of notation, this is called pi, the probability of the ith symbol. And so the first symbol would probably be A, and so P1 would be the probability of getting an A for a given character. And BI will be the number of bits. The number of bits used to represent the ith symbol. Okay, so A occurs a lot here, and so we're going to want to make BI smaller. It's just more efficient. If something occurs a lot, use fewer bits to encode it, right? And, okay, this is hopefully pretty familiar. And so the expected number of bits per symbol is this. You take the probability of each symbol times the number of bits for that symbol, and that gives you the expected value. Now, the number of bits are constrained as follows by this equation. In order for, so I guess this relates to if you have a tree, then you can represent that as a 0, 1, and then 0, 1, and maybe we put our A here, and maybe we put an O here, because O occurs quite a bit, and then 0, 1 again, and and so on. And so you can see, okay, dot, dot, dot. And you can see it's the leaves here that represent actual characters, right? And the paths, like 0, 0, 0, 1, those represent the bits that are used. And so you can imagine going down this tree with a probability of 1/2 of going down in each direction. And then you'll see that 1/2 to the number of bits, if we add that up over all the symbols, we're going to get this constraint, that overall the probability is less than 1, and which means the sum of those is less than or equal to 1. If we wanted to, of course, we could use 1/3 and 2/3, and we get other interesting results. But let's keep it symmetric, so we can just have the number of bits rather than the number of zeros and the number of ones. So, yeah, so we get a simple constraint there. There's also other constraints, right? But we're going to ignore those. Basically, bits are discrete, they're integers. Here, we're ignoring that. We're making everything nice and continuous and easy to analyze. And since these sum to less than or equal to 1, we can think of them kind of like a probability. And so I'm going to call that Qi. And so then the number of bits is equal to this, just solving this equation for Bi. We take the log, and then we need to transfer the negative to solve for Bi. And so really we want to minimize this, where now the sum of the Qi could be less than or equal to 1. Of course it's going to be 1 if we try to actually minimize this. Yeah, so this is starting to look kind of similar to the entropy, right? So anyways, we want to pick the optimal Qi. Since the Qi sum to 1, that means the derivative with respect to each Qi has to be the same. So that if we take a little bit of probability from one of the Qi's and add it to another, we don't change anything. That's why all the derivatives have to be the same. And it looks like I didn't actually do the work here, but we're going to get, if you take the derivative with respect to Qi, we're going to get minus Pi over Qi equals K. And since this is independent of I, this means that pi, all right. And so we can see, since the pi is sum to 1 and the qi is also sum to 1, so pi is proportional to qi, and since they all sum to 1, actually pi has to be equal to qi, which is what we have here. Cool. So, so we figured out the qi, and therefore the number of bits is just going to be equal to minus the log of pi, because qi is pi, right? So I want to write that in. Therefore, for symbol I, we should use bi equals minus log of pi bits. Okay. Therefore, the total, the minimum space needed, given these continuous approximations, is sum over I of minus pi log pi. Just plugging that back into here. And this is what we call the entropy. And by the way we derive this, we can see if you have your probability spread out over more different symbols, then the entropy would increase, right? So that's like from physics, that agrees with my understanding of entropy. Yeah. So this is, yeah. I didn't understand what entropy meant when I was coming up in computer science before. Now, an intuition for what's going on here is, say A and B are half as likely as C. Then, in the way that you drive Huffman codes, you can combine A and B and treat them as a single character, AB, which is now just as likely as C. So, obviously we should use the same number of bits for the character AB as for C. And then, to distinguish between A and B, you need one more bit, right? Which means that, yeah, so each time the probability halves, we use one more bit on average, right? So if we allow bits to be continuous, then this will be exactly true. Right. And this is just another way of looking at it. I'm not totally sure of the significance. But according to this tree, if we imagine the chance of going down each branch, if we imagine that that is 1/2, then we could generate characters from this tree, right? If we 1/2, 1/2, with a quarter probability, we'll generate an A. Say we've got a C here. We'd have to get a 1, and we'd have to go here, here, here. So with a probability 1/8, we'll generate a C, and so on. So this tree, assuming you've got 50-50 chance of going in each direction at each fork, it basically defines the probabilities pi. And yeah, and you could use it to generate a sequence of characters according to those probabilities. What is the most efficient way, once we've generated those characters, what's the most efficient way to store the sequence? Well, it's this same tree, in fact, that generated it. So, yeah, I found that kind of interesting. don't think I have anything else to say about that. So, yeah, so entropy is the important thing to understand underlying the KL divergence, which we'll go over in the next screencast. And in fact, the KL divergence, we'll be looking at how different is this going to be from the minimum when Qi is not equal to Pi. Thanks for watching.